Nancy Grace Roman Space Telescope. The Nancy Grace Roman Space Telescope, shortened as the Roman Space Telescope, Roman, or RST, is a future National Aeronautics and Space Administration, NASA, infrared space telescope in development and scheduled to launch to a Sun-Earth L2 orbit in September 2026. It is named after former NASA Chief of Astronomy Nancy Grace Roman. The Nancy Grace Roman Space Telescope, NGRST, is based on an existing 2.4 meters, 7.9 feet, wide field of view, FOV, primary mirror and will carry two scientific instruments. The Wide Field Instrument, WFI, is a 300.8 megapixel multiband visible and near-infrared (NIR) camera, providing a sharpness of images comparable to that achieved by the Hubble Space Telescope, HST or Hubble, over a 0.28 square degree field of view, 100 times larger than imaging cameras on the Hubble. The Coronagraph Instrument, CGI, is a high-contrast, small field of view camera and spectrometer covering visible and near-infrared wavelengths using novel starlight-suppression technology. Stated objectives include a search for extrasolar planets using gravitational microlensing, along with probing the chronology of the universe and growth of cosmic structure, with the end goal of measuring the effects of dark energy, the consistency of general relativity, and the curvature of spacetime. The Nancy Grace Roman Space Telescope was recommended in 2010 by the United States National Research Council, NRC, Decadal Survey Committee as the top priority for the next decade of astronomy. On February 17, 2016, it was approved for development and launch. On May 20, 2020, NASA Administrator Jim Frederick Bridenstine announced that the mission would be named the Nancy Grace Roman Space Telescope in recognition of former NASA Chief of Astronomy Nancy Grace Roman's role in the field of astronomy. As of May 2024, Roman is scheduled to be launched on a SpaceX Falcon Heavy rocket under a contract specifying readiness by October 2026, supporting a NASA launch commitment of May 2027. As of January 2026, the launch is expected to occur no earlier than September 2026. Development of mission. The design of the Roman Space Telescope shares a heritage with various proposed designs for the Joint Dark Energy Mission, JDM, between NASA and the Department of Energy, DOE. The original design, called the Wide Field Infrared Survey Telescope, WFIRST, Design Reference Mission 1, was studied in 2011 to 2012, featuring a 1.3 meters, 4.3 feet, diameter unobstructed 3-mirror and astigmat telescope. It contained a single instrument, a visible to near-infrared imager slitless prism spectrometer. In 2012, another possibility emerged. NASA could use a second-hand National Reconnaissance Office, NRO, telescope made by Harris Corporation to accomplish a mission like the one planned for the Wide Field Infrared Survey Telescope. NRO offered to donate 2 telescopes, the same size as the Hubble Space Telescope, but with a shorter focal length and hence a wider field of view. This provided important political momentum to the project, even though the telescope represents only a modest fraction of the cost of the mission and the boundary conditions from the NRO design may push the total cost over that of a fresh design. This mission concept, called First AFTA, Astrophysics Focused Telescope Assets, was matured by a scientific and technical team. This mission is now the only present NASA plan for the use of the NRO telescopes. The Roman baseline design includes a coronagraph to enable the direct imaging of exoplanets. Several implementations of WFIRST Roman telescope were studied. These included the Joint Dark Energy Mission Omega configuration, an interim design reference mission featuring a 1.3 meters, 4.3 feet, telescope, design reference mission 1 with a 1.3 meters telescope, design reference mission 2 with a 1.1 meters, 3.6 feet, telescope, and several iterations of the AFTA 2.4 meters, 7.9 feet. Configuration. In the 2015 final report, Roman was considered for both geosynchronous orbit and for an orbit around the Sun-Earth Lagrange point L2. L2 has disadvantages versus geosynchronous orbit in available data rate and propellant required, but advantages for improved observing constraints, better thermal stability, and more benign radiation environment. Some science cases, such as exoplanet microlensing parallax, are improved at L2, but the possibility of robotic servicing at either of the locations is currently unknown. By February 2016, it had been decided to use a halo orbit around L2. The project is led by a team at NASA's Goddard Space Flight Center, GSFC, in Greenbelt, Maryland. On November 30, 2018, NASA announced it had awarded a contract for the telescope. This was for a part called the Optical Telescope Assembly, OTA, and runs to 2025. This is in conjunction with the Goddard Space Flight Center, for which the OTA is planned for delivery as part of this contract. A February 2019 description of the mission's capabilities is available in a white paper issued by members of the Roman team. During the 2025 federal government shutdown, NASA's Goddard Space Flight Center began closing multiple buildings and consolidating equipment, which the agency describes as a pre-planned, strategic consolidation, not expected to impact missions. A NASA spokesperson told CNN that work on the Nancy Grace Roman Space Telescope and the Dragonfly mission would continue during the shutdown as accepted operations. According to Space.com, some employees at the center expressed concern that the manner and timing of the closures could disrupt work on those projects, and CNN reported that an internal document compiled by Goddard staff cited potential impacts on specialized testing laboratories. Science objectives. The science objectives of Roman aim to address cutting-edge questions in cosmology and exoplanet research, including answering basic questions about dark energy, complementary to the European Space Agency, ESA, Euclid mission, and including, is cosmic acceleration caused by a new energy component or by the breakdown of general relativity on cosmological scales? If the cause is a new energy component, is its energy density constant in space and time, or has it evolved over the history of the universe? Roman will use three independent techniques to probe dark energy: baryon acoustic oscillations, BAO, observations of distant supernovae, and weak gravitational lensing. Completing a census of exoplanets to help answer new questions about the potential for life in the universe. How common are solar systems like our own? What kinds of planets exist in the cold, outer regions of planetary systems? What determines the habitability of Earth-like worlds? This census makes use of a technique that can find exoplanets down to a mass only a few times that of the Moon, gravitational microlensing. The census would also include a sample of free-floating planets, FFPs, with masses likely down to the mass of Mars. Establishing a guest investigator mode, enabling survey investigations to answer diverse questions about our galaxy and the universe. Providing a coronagraph for exoplanet direct imaging that will provide the first direct images and spectra of planets around our nearest neighbors, similar to our own giant planets. Detection of primordial black holes, PBHs. Instruments. The telescope is to carry two instruments. Both were installed into the telescope in December 2024. WFI. The Wide Field Instrument, WFI, is the primary science instrument for the mission. It is a 300.8 megapixel camera, providing multiband imaging and spectroscopy from the visible to NIR, near-infrared, 0.48 to 2.30 micrometers. 8 science filters, 1 wide band, and 7 more narrow filters, provide high-quality images in subsets of the total spectral bandwidth of the instrument. It also carries both a high-dispersion GRISM and lower-dispersion PRISM assemblies for wide-field slitless spectroscopy. A dark element, made out of spectralon, can block out the light from space and reflect calibration light onto the detector. The 8 filters, 2 spectroscopy elements, and dark element are all attached to an element wheel assembly, EWA, that rotates one element at a time into the active position. This enables the scientists to choose which colors of light are needed for each mission, or switch between imaging and spectroscopy modes. A HGCDT-based, chemical compound of mercury telluride, HGTE, and cadmium telluride, CDTE, focal plane array, FPA, captures a 0.28 square degree field of view with a resolution of 0.11 arcseconds. The detector array is composed of 18 HGCDT 4K x 4K photodiode arrays, H4RG10 detectors, provided by Teledyne Technologies Incorporated. The instrument carries onboard calibration capability to help the scientists discern the subtle changes in images from their dark matter mission compared to ordinary distortions of the optics or of the FPA. The FPA is attached to a set of hexapod actuators that can reposition the focal plane into the best focus position based on analysis from the ground to ensure the captured images are always of high quality over the lifetime of the mission. WFI was completed and shipped to NASA in August 2024. CGI. The Coronagraph Instrument, CGI, is a high-contrast coronagraph covering shorter wavelengths, 575 to 825 nanometers, using dual deformable mirror starlight suppression technology. It is intended to achieve a part per billion, ppb, suppression of starlight to enable the detection and spectroscopy of planets with a visual separation of as little as 0.15 arcseconds from their host stars. CGI is intended as a technology demonstrator for an exoplanet imaging instrument on a future large space-based observatory, such as the Habitable Worlds Observatory, HWO. History. On March 2, 2020, NASA announced that it had approved NGRST telescope to proceed to implementation, with an expected development cost of $3.2 billion and a maximum total cost of $3.934 billion, including the coronagraph and 5 years of mission science operations. On March 31, 2021, the NASA Office of Inspector General, OIG, released a report that stated that the development of the Nancy Grace Roman Space Telescope had been affected by the COVID-19 pandemic, which hit the U.S. during a particularly important time in the telescope's development. NASA is expecting a total impact of $400 million due to the pandemic and its effect on subcontractors for the project. On September 29, 2021, NASA announced that Roman had passed its Critical Design Review, CDR, and that with predicted impacts from COVID-19 disruptions, and with flight hardware fabrication completed by 2024 followed by mission integration, the launch date would be no later than May 2027. On July 19, 2022, NASA announced that Roman would be launched on a Falcon Heavy launch vehicle, with a contract specifying readiness by October 2026 and a launch cost of approximately $255 million. In September 2024, the satellite bus which will carry the telescope, was substantially completed. The following December, the instruments and mirror assembly were successfully integrated onto a section called the instrument carrier. In October 2024, the telescope passed a major spin test. The Space Telescope had finished construction on November 25, 2025. Institutions, partnerships, and contracts. The Roman Project Office is located at NASA's Goddard Space Flight Center in Greenbelt, Maryland, and holds responsibility for overall project management. GSFC also leads the development of the Wide Field Instrument, the spacecraft, and the telescope. The Coronagraph Instrument is being developed at NASA's Jet Propulsion Laboratory, JPL, in Pasadena, California, USA. Science support activities for Roman are shared among the Space Telescope Science Institute, STSCI, in Baltimore, Maryland, which is the Science Operations Center, the Infrared Processing and Analysis Center, IPAC, in Pasadena, California, and Goddard Space Flight Center. Partners. For international partners, namely the French National Space Agency (NIS), European Space Agency, Japan Aerospace Exploration Agency, JAXA, and the Max Planck Institute for Astronomy, MPAA, have joined with NASA to provide various components and science support for Roman. Beginning in 2016, NASA expressed interest in ESA contributions to the spacecraft, coronagraph and ground station support. For the coronagraph instrument, contributions from Europe and Japan have been established. In 2018, a contribution from Germany's Max Planck Institute for Astronomy was under consideration, namely the filter wheels for the star-blocking mask inside the coronagraph. In 2016, the Japanese Aerospace Exploration Agency proposed to add a polarization module for the coronagraph, plus a polarization compensator. An accurate polarimetry capability on Roman may strengthen the science case for exoplanets and planetary disks, which shows polarization. Ground support will be provided by a new NASA station in White Sands Test Facility, WSTF, in New Mexico, the Ms. Deep Space Station, MDSS, in Japan and ESA's new Norcia Station, also known as NNO, in Australia. Construction contracts. In May 2018, NASA awarded a multi-year contract to Ball Aerospace and Technologies Corporation, commonly Ball Aerospace, now called BAE Systems Space and Mission Systems, to provide key components, the optomechanical assembly, for the Wide Field Instrument on Roman. In June 2018, NASA awarded a contract to Teledyne Scientific and Imaging to provide the infrared detectors for the Wide Field Instrument. On November 30, 2018, NASA announced it had awarded the contract for optical telescope assembly to the Harris Corporation of Rochester, New York. Via an agreement signed in June 2022, MPIA designed, built, and provided all of CGI's precision alignment mechanisms, PAM, which operate, stabilize, and control optical elements such as optical filters.